Gang, we're going to talk about polarization. We talked about charge polarization before. We talked about like negative being on one side of a molecule, positive on another. Polarization in this sense is altogether different. We're talking about the lineup of waves. If I take a rope and tie it to the wall, and I shake the rope up and down like this, guess which way the wave will vibrate? How many say, oh, probably like this? Come on, trick question. No. If I shake it up and down like that, the rope will vibrate like that. And the vibration is aligned. We don't say aligned, we say it's polarized. If I shake the rope back and forth horizontally, then I'll generate a horizontally polarized wave. Okay? You saw the example in the textbook. If I pass these waves through a picket fence, maybe the picket fence can filter them out. It turns out if I have a picket fence where the fence staves are all vertical, and I have vertical openings, and I shake my rope and it goes right through the opening, it's like the opening weren't there. The shake goes right on through, and the wave travels. And that's easy to see. This is very conceptual. If I take the rope and shake it sideways, however, whoom, the vibration can't get through the fence. And so what the fence does is blocks it. And so that's a filter. And I have over here such a thing. Here's a polarization filter. Okay? And that's what this is. This will allow light to vibrate through going only one way, not another way. I don't know what the plane of this is. I can't see. But let's suppose it's like this. I have microscopic picket fences like that. I have in the back here a piece of white material that will diffuse light so that when I shine light through it, there won't be too much glare. But nevertheless, this is a piece of Polaroid filter. And let me tell you how this came to be. It turns out that non-cubic shaped crystals, all non-cubic crystals, say something like this, sort of like a diamond shape. All non-transparent crystals will pass light in two directions, the two preferred directions. The crystalline structure is sort of like an orange grove. You ever drive by an orange grove, you see all these trees, you see right down? And you're driving again, right down the cleaves, okay? There's certain preferred paths. Well, it turns out light will go through vibrating like this, and light will go through vibrating like that. And over here, no, you'd only get components here and components here. And it turns out in most crystals, the vibrations in one direction go through quicker than the vibrations in the other. So it's a little time delay. And you get beautiful colors as a result of that. Get into that a little bit later. But for now, there are some crystals that take this one here and cut it right down, and it's absorbed. This was known at the first part of the century. A lot of people knew that there were needle-shaped crystals that would pass light in only one direction only. A fellow by the name of Edwin Land knew about that and did something about that. What Edwin Land did was took all these crystals, this crystalline material, made it into sort of like a jelly, put it on some cellophane, and stretched it. And when he stretched the cellophane, guess what these things here did? What would happen if you had a whole bunch of needles on a piece of plastic, and they point every which way? And you take and you stretch the plastic out. What will the needles do, gang? Won't they kind of all line up? That's what Land did, and they got them all to line up. Then what he did is he put it down, he put another piece of plastic on top, took his wife's iron, and ironed it, and cemented those needles together, and made more than $1 million. Edwin Land patented it, and these are Polaroid filters, and that's what they, in a sense, are. Is they're made up of molecules in here, which are crystals or molecules that are all lined up in one direction and will allow the light to pass through one way.